Welcome to the deep dive. Today, we're tackling something really fundamental, actually, based on your requests. How has science itself, the process of discovery, changed over time?
It's a great topic. You sent over some really interesting material outlining these different paradigms of scientific progress.
Exactly, paradigms. So our mission today is to kind of unpack those, figure out what makes each one distinct, and spotlight the key moments and people involved.
It really is a fascinating story of how our methods for understanding the universe have gotten, well, increasingly sophisticated.
Okay, so the sources lay out four main paradigms, right? With maybe a fifth one starting to take shape now.
That's the framework, yes. Four established plus one emerging.
First up is empirical observation. Basically, seeing is believing, direct experience.
The foundation, really. Then you get theoretical models.
Right, creating abstract frameworks, often using math to explain things.
Third is computational simulations, using computers to model really complex stuff.
Stuff you can't easily experiment on or theorize about directly.
Precisely. And fourth is data-intensive science, pulling knowledge out of just massive amounts of data.
The data deluge era.
You got it. And finally, this emerging fifth one, AI-based science, where artificial intelligence and machine learning are becoming central to research.
Wow, okay. So each one builds on the last, adding new tools.
Exactly. New tools, new perspectives, expanding our toolkit for discovery.
Cool. So our goal for this deep dive is to walk through the history, the big names, the major contributions for each paradigm, give everyone a clear picture of this evolution, and hopefully some of those aha moments along the way.
Sounds good. It's a journey worth taking.
So where do we start? Logically, paradigm one?
Logically, yes. Empirical observation. This really got going during the scientific revolution, I think 16th, 17th centuries.
Right, the scientific revolution, that was a massive shift, wasn't it? Moving away from just like philosophical arguments or religious dogma.
Absolutely. A huge shift towards actually looking at the world, experimenting. Before that, a lot of science was based on, what Aristotle said or what fit with theology.
But then people started prioritizing direct observation.
Exactly. Thinkers like Galileo, Isaac Newton later on, they put observation and experiment front and center. Galileo and his telescope, Newton needing observations for his laws, prime examples. It laid the foundation for the scientific method we use today.
Okay, let's talk Galileo. The material calls him the father of modern observational astronomy. What made his approach so different?
Well, the key thing was his systematic use of the telescope starting around 1609. He heard about this new invention, built his own, and made it way better, magnifying things up to 20 times.
20 times? That must have just opened up a whole new view of the heavens. What did he actually see up there?
Oh, incredible things that shattered old ideas. He saw the moon wasn't a perfect orb, it had mountains and craters. He found Jupiter's 4 largest moons orbiting it, not Earth.
Like a mini solar system.
Exactly. And he observed the phases of Venus, which only made sense if Venus orbited the sun.
So his observations directly contradicted the accepted Earth-centered model.
Precisely. It wasn't just seeing new things. It was seeing things that provided hard, empirical evidence against centuries of theory. Evidence for Copernicus's heliocentric model. His insistence on observation, even when it was controversial, was revolutionary.
He really challenged the status quo, paved the way for others, I guess.
Absolutely. People like Kepler and Newton built directly on his observational groundwork.
Okay, speaking of meticulous observers, the material also highlights Tycho Brahe. He was a bit earlier, right, and didn't really use telescopes for most of his work.
That's right. Brahe was all about incredibly precise measurements with the naked eye, or, well, with large sighting instruments, but pre-telescope mostly. He spent decades just painstakingly recording the exact positions of stars and planets.
So he was building this massive database of the sky just through sheer observational effort.
Incredible effort, yeah. He compiled this unparalleled data set, unbelievably accurate for the time.
And that data became crucial later.
Hugely important. Johannes Kepler used Brahe's detailed observations, couldn't have done it otherwise, to figure out his laws of planetary motion, like the fact that planets move in ellipses, not perfect circles.
So Galileo showed the power of new tools for observation, while Brahe showed the power of just meticulous long-term observation.
A great way to put it. Brahe's legacy is really about the fundamental importance of precise measurement and building that solid empirical evidence base.
Okay, now alongside these astronomers, we have Francis Bacon, the philosopher. How does he fit into this empirical picture?
Bacon was crucial for laying out the philosophy behind the empirical method. His book, Novum Organum, The New Instrument, argued for a whole new system of logic based on collecting data systematically through observation and experiment.
So he wasn't necessarily doing the observing, but he was defining how it should be done, like the intellectual framework.
Exactly. He championed inductive reasoning, starting with specific observations and building up to general principles. That was a contrast to the older deductive way, which often started with general theories and tried to fit observations into them. Observe first, theorize later. Makes sense.
And he was very critical of relying too much on old texts without checking against reality.
Didn't he also talk about biases?
Yeah.
The idols of the mind? That sounds really modern.
Extremely modern. Yes, he identified these idols as obstacles to objective thinking. Idols of the tribe biases common to all humans. Idols of the cave are personal biases from upbringing and experience.
Okay.
Idols of the marketplace problems arising from the limits and ambiguities of language. You know how misunderstandings happen just because words mean slightly different things to different people?
Yeah, all the time.
He argued that could mess up scientific reasoning too. And finally, idols of the theater biases from sticking dogmatically to old philosophical systems.
Wow. Recognizing those seems like the first step to overcoming them. That was his point, to create a more disciplined, objective approach to science. He also had this vision of science as collaborative, cumulative, not just lone geniuses, but people working together, sharing results, building knowledge over time.
Like research institutions.
Exactly. His ideas really laid the groundwork for the way modern science is organized.
So this empirical paradigm wasn't just astronomy. The material mentions biology too. Carl Linnaeus.
Yes, Linnaeus and his system for classifying living things taxonomy. That's a perfect example of meticulous observation leading to a major scientific framework, observing, describing, categorizing thousands of species based on shared characteristics.
So observing but also organizing the observations systematically.
Precisely. And that emphasis on observation and description flowed into education too. Lab work, field studies, they became central to how science is taught.
And technology was a driver too, right? Telescopes, microscopes.
Definitely. New instruments kept expanding what we could observe, opening up new scientific frontiers constantly.
It seems intuitive that results you can actually see are easier for the public to grasp too.
Generally, yes. Tangible results can be more convincing than abstract theories.
But there are limits, right? You can't observe everything. Our senses aren't perfect. Bias is always a risk.
Absolutely crucial point. Observational bias is a constant challenge. We tend to see what we expect to see. And some things are just too small, too far away, or too complex to observe directly.
So how do scientists deal with that?
Well, things like blind and double-blind experiments help mitigate bias. But often you have to rely on indirect evidence, or move towards simulations or theoretical models to understand things you can't directly see.
Which leads us nicely to the second paradigm, theoretical models. Building on observation but trying to explain the why.
Exactly. Paradigm 2 is about creating abstract, often mathematical, frameworks to explain the underlying principles governing what we observe. This really took off in the 18th and 19th centuries.
And Isaac Newton is the giant here, right? His Principia Mathematica, laws of motion, universal gravitation.
Absolutely monumental. His 3 laws of motion basically defined classical mechanics, replacing older Aristotelian ideas. Inertia, EFMA, action-reaction, still fundamental.
And he developed calculus to express these ideas mathematically. That's a huge step towards abstraction.
A massive leap. Calculus provided the language needed to model change, to make precise predictions. It shifted science from just describing what happens to explaining how and why using mathematical laws.
And universal gravitation explaining apples and planets with the same rules. That's unification.
Incredible unification, yeah. Linking celestial and terrestrial mechanics under one framework. It wasn't perfect, couldn't quite explain Mercury's orbit, for instance, but it dominated physics for centuries.
Until Einstein. But before him, James Clerk Maxwell, unifying electricity and magnetism.
Another giant leap in theoretical modeling. Maxwell's equations showed electricity and magnetism weren't separate forces, but aspects of one underlying electromagnetic field.
And light itself is part of that,
Right.
an electromagnetic wave.
That was the stunning insight. His theory predicted these waves travel at the speed of light, fundamentally changing our understanding of light and paving the way for technologies like radio.
And his theory then got tested experimentally, right? Hertz and Marconi.
Yes, a perfect example of theory predicting something and experiments confirming it, leading to technology. That interplay is key.
Then comes Einstein, special and general relativity, redefining space and time themselves.
A whole new level of abstraction. Special relativity gave us space-time, EMC-SAP, mass-energy equivalence. Mind-bending stuff.
And general relativity changed how we see gravity.
Completely. Not a force pulling things, but the curvature of space-time caused by mass and energy. It explained things Newton's theory couldn't, like Mercury's orbit predicted gravitational lensing. It's a best model of gravity on large scales.
Impact in cosmology, black holes, the expanding universe, huge implications.
Absolutely. And then in the quantum realm, Niels Bohr played a similar role.
Right, the atomic model. Electrons in specific energy levels.
Bohr's model was radical for its time. It explained why atoms emit specific colors of light. He introduced the idea of electrons in discrete orbits and the principle of complementarity things acting like waves and particles.
Which paved the way for Schrödinger's equation and Heisenberg's uncertainty principle, the core of quantum mechanics.
Exactly. His theoretical insights were foundational for understanding the subatomic world, which is deeply counterintuitive and requires abstract models.
So this theoretical paradigm gave us fundamental physics, but it wasn't just physics, right? Chemistry, biology.
Oh, definitely. Think Dalton's atomic theory in chemistry, Mendel's periodic table organizing principles based on underlying theoretical ideas. Later, quantum chemistry explained chemical bonding.
And in biology, Darwin.
Darwin's theory of evolution by natural selection is a cornerstone theoretical model, later integrated with genetics in the modern synthesis. Population genetics models like Hardy-Weinberg, and of course Watson and Crick's DNA double helix structure, a model explaining heredity.
Even things like modeling disease spread, ecosystems, neural networks.
Yes, Surin models for epidemics, Lotka-Volterra for predator-prey, Hodgkin-Huxley for neurons, all theoretical frameworks.
And economics, too. Supply and demand, game theory.
Absolutely. Economics relies heavily on theoretical models. Supply-demand, game theory's Nash equilibrium, macroeconomic models like ISLM, even financial models like Black-Scholes. Behavioral economics, Kahneman and Tversky's work, too.
So these models, even if simplifications, help us understand complex systems across so many fields.
They provide the essential lens for analysis and prediction.
And educationally, teaching these models must have pushed analytical thinking.
For sure. Fostered abstract reasoning. And the math needed spurred development of new tools.
And even early computer simulations, bridging to the next paradigm.
Exactly. The complexity started demanding more computational power.
And successful predictions from these models probably helped public understanding. Climate science, maybe?
When models make accurate predictions, it builds confidence and can demystify complex science.
But again, limitations, over-reliance. Models aren't perfect reality. Validation is hard.
Crucial caveats. Models are simplifications. Validation, especially for complex ones, is a major challenge. We always need empirical checks.
Which brings us neatly to paradigm 3, computational simulations, using machine power to tackle that complexity.
Right. This paradigm really bloomed mid-20th century with the arrival of powerful computers like ENIAC, UNIVAC. Suddenly, calculations that were impossible became feasible.
Scientists saw the potential right away. Von Neumann.
John von Neumann was key.
Yeah.
He saw computers weren't just for military calculations, but for fundamental research. He was involved in early climate modeling attempts, for example.
And Richard Feynman, the physicist, he advocated for computation, too, even in biology.
Feynman was a visionary. He knew many physical systems were just too mathematically complex to solve by hand. Simulations offered a way forward. He saw applications in fluid dynamics, particle physics, and yes, even computational biology early on.
And Stanislaw Ulam and Monte Carlo methods. That sounds intriguing. Using randomness.
It's a powerful idea. Ulam popularized it during the Manhattan Project. Instead of trying to calculate every possibility, you use repeated random sampling to estimate the outcome. Great for problems with uncertainty.
Like neutron diffusion or finance or engineering.
Exactly. It's incredibly versatile and still widely used, constantly be refined.
And Kenneth Wilson's work on phase transitions, using computers to understand why different things behave similarly near boiling points or freezing points.
Wilson's renormalization group theory was groundbreaking and heavily reliant on computation. It helped explain this universality in critical phenomena. He really pioneered using computers as essential tools in theoretical physics.
So computation opened up new research areas. Climate science seems like a huge beneficiary.
Absolutely central. General circulation models, regional climate models, these are massive simulations integrating physics, chemistry, biology to predict climate patterns and change. Indispensable now.
And physics uses it across the board, from quantum to cosmology.
Everywhere. Simulating particle collisions, fluid flow, material science, galaxy formation, tasks that are often impossible experimentally or analytically.
Biology, too. Systems biology, genomics, epidemiology.
Increasingly vital. Modeling complex cellular networks, protein folding, population dynamics, disease spread, even brain activity.
And engineering must rely heavily on simulations for design and testing.
Oh, massively. Finite element analysis for structures, computational fluid dynamics for airflow thinking, designing planes, cars, buildings. It saves huge amounts of time and money compared to building physical prototypes for everything.
So this required new algorithms, numerical methods, and pushed high-performance computing.
Definitely. A whole field of computational science emerged, developing the methods and needing faster machines.
But validation remains critical, making sure the simulation matches reality.
Absolutely paramount. You constantly need to check simulations against experimental data. Verification, making sure the code is right. Validation, making sure the model reflects reality. Both are essential.
And like the others, this changed education teaching, coding, simulation skills, and the visualizations help public understanding.
Yes, computational literacy is now a core scientific skill. And seeing a complex process simulated visually, like climate change impacts, can be very powerful for communication.
But the challenges persist. Over-reliance, model validation difficulties, computational limits.
Always. Simulations are tools, not truth machines. Ensuring their reliability, understanding their limits, and having the resources, power, storage, expertise are ongoing challenges.
Okay, paradigm 4, data-intensive science, driven by the sheer explosion of data this century.
Exactly. Digital sensors, gene sequencing, the internet. We're swimming in data. This paradigm is about developing ways to store, manage, analyze, and extract knowledge from these massive data sets.
Like the Human Genome Project or the Large Hadron Collider, generating unbelievable amounts.
Perfect examples.
Yeah.
They necessitated new approaches. Science, as some call it.
Jim Gray is mentioned as a key visionary here, his fourth paradigm idea.
Gray was hugely influential. A database expert who saw that science was fundamentally changing because of data volume. He championed tools and infrastructure for this new way of working, advocating for open data too.
And Hector Garcia-Molina's work on distributed databases sounds crucial for handling data spread across many systems.
Absolutely. Ensuring data consistency and reliability when it's not all in one place is a massive technical challenge that Garcia-Molina made significant contributions to, essential for large collaborations.
And John Chambers, creator of S, the precursor to R, providing the tools for analysis.
Right. R and Python, with its libraries now too, provides the flexible environment scientists need to manipulate, visualize, and model these large, complex data sets. Chambers' work democratized sophisticated data analysis.
So the data itself becomes the source of discovery. Genomics seems like a prime example.
A revolution driven by data. Next-gen sequencing generates oceans of data. Analyzing it lets us find disease genes, understand genetic variation, move towards personalized medicine. Bioinformatics is key.
Astronomy, too, with huge surveys mapping the sky.
Massive digital sky surveys. SDSS, LSST coming online, soon generate petabytes. Machine learning is now essential for finding patterns, classifying galaxies, discovering planets in that data flood.
Environmental science must be using this, too. Satellite data, climate models, sensor networks.
Definitely. Integrating data from satellites, ground sensors, ocean buoys, climate model outputs. It allows for a much more comprehensive understanding of Earth systems and environmental change.
And even the social sciences, analyzing social media, survey data.
Yes, exploring patterns in human behavior and societal trends using large data sets from online activity, digital records, large surveys. It brings new opportunities, but also challenges about interpretation and bias.
So this paradigm shifted focus to data management, analysis skills, machine learning, and technology like cloud computing became essential.
Absolutely. You need the infrastructure for storage and processing and the analytical techniques. Data science skills are now in demand everywhere, and good visualization is key for making sense of it all.
But challenges here too. Data bias is a big one. Privacy, ethics.
Huge concerns. If your data is biased, your conclusions will be too. Protecting privacy is critical, especially with personal data. And the ethical use of data, who owns it, how is it used, needs constant attention.
Which leads us to the fifth, emerging paradigm, AI-based science. Taking data science and adding intelligent automation.
That's a good way to think about it. AI is being integrated more deeply, automating tasks, finding incredibly subtle patterns, handling complexity that even big data tools struggle with, and potentially learning continuously.
Automating things like data collection, analysis in genomics, or climate science.
Yes, AI can automate laborious parts of the pipeline, managing complex data streams in climate science, analyzing sequences in genomics, high-throughput screening and drug discovery, freeing up researchers.
And pattern recognition goes to another level, finding things humans might miss.
AI, especially deep learning, excels at finding complex, nonlinear patterns in massive datasets, predicting weather, identifying anomalies in astronomical data, diagnosing diseases from images.
And handling complexity,
Yeah.
modeling intricate biological systems or climate interactions.
Exactly. AI models can potentially capture the interactions of many variables in systems like cellular pathways, ecosystems, economies, or the brain in ways traditional models struggle with.
Driven by advances in AI itself. Deep learning, reinforcement learning, generative models.
Those are the engines. Deep neural networks for unstructured data. Reinforcement learning for finding optimal strategies. Generative models like GANs for creating new data, simulating galaxies, designing molecules.
And applications are already widespread. Healthcare, material science.
Rapidly growing. Medical image analysis, drug discovery, materials design, environmental monitoring, financial modeling. It's touching almost every field.
But explainable AI is becoming important. Understanding why the AI makes a decision.
Crucial. These models can be black boxes. We need methods to understand their reasoning, especially in high-stakes areas like medicine, to ensure they're fair, reliable, and trustworthy.
So the future involves better AI algorithms, maybe learning from less data, integration with quantum computing or IoT.
That seems likely. More efficient learning, better generalization, understanding causality, not just correlation. Integrating AI with other tech holds huge potential.
And interdisciplinary work in ethics remains central.
Absolutely essential. Collaboration is key. And addressing bias, ensuring fairness, transparency, privacy, accountability. These ethical considerations have to be front and center as AI becomes more powerful in science.
Wow, what a journey. From simply looking carefully at the world to potentially having AI partners in discovery.
It really shows the accelerating pace of change in how we do science, each paradigm adding powerful new capabilities.
Hopefully this deep dive has given everyone listening a clearer map of that evolution, highlighting the key shifts and maybe sparking some of those aha moments about how we know what we know.
Understanding the journey helps appreciate the tools we have now and their foundations.
So looking ahead at this AI-driven fifth paradigm, what breakthroughs do you think might be on the horizon? And what are the biggest ethical tightropes we need to walk as AI gets woven deeper into science?
That's the big question, isn't it? The potential seems immense, but so are the responsibilities. It's definitely a landscape to watch closely.
Food for thought indeed. Thanks for joining us on this deep dive.